Hi, I'm Francesca, and today with Caroline we're going to represent Group 19 in presenting the final project for process mining.
The dataset used is the BPI Challenger 2012 containing data about a loan application process. The Eindhoven University of Technology provided this dataset. It is sorted in an XCS event log format, which is an XML-based format specifically made for event logs. With the self-made XCS parser, we were able to open and convert it to CSV files, which made it possible for every member in the group to work with this data. The CSV file contains 7 columns, 214,377 entries. It has columns like event ID, event time, and case concept name. For the pre-processing, various features were added, such as event position by grouping the events by the case, and then cumulative counting over the amount of events in a case. Additionally, a second feature showing the duration of the event by getting the time difference between the two events was added, as well as a feature displaying the elapsed time since the beginning of the case by the naive estimator is the baseline estimator. The baseline estimator was trained by selecting the most succeeding event Y of event X. For example, for A submitted, the most succeeding event is A partially submitted. For time estimation, it selects the average time difference between event X and Y for every event X. For example, for A submitted, the average time is 582.64 milliseconds.
Our second model is a compact prediction tree. It's a prediction tree which losslessly compresses all training sequences. In a training phase, a prediction tree is built, followed by the prediction phase, in which in the first step, similar sequences are found using inverted indexing. A lookout table, which contains the terminal node of each sequence, is used to determine the elements suitable for prediction, for which a decision is based on considerations such as the number of similar sequences, frequency of the respective prediction elements, and a number of previous prediction elements. Thus, we use a list of all subsequences starting from the first element of all event traces of the training set to predict the next event for each entry of the test set. The model predicts on case-based features from the column event concept name. To summarize, in a training phase, a prediction tree is built using subsequences of event names, starting from the initial position of every trace as a chosen feature. Prediction is made by finding sequences similar to the target sequence in a tree. In this way, the predicted event cannot be an event previously seen in a target subsequence. Additionally, this model was chosen as one of the models for event prediction because it's a trade-off between high accuracy and time efficiency and suitable for sequential data.
Our third model was an LSTM model. LSTM models have cells that are able to retain information over a longer period. Therefore, we tried to predict the time and events with it. To train the model, we created a new column called Next, which contains the next event of a certain event in the same case. We use the current event column as a feature value, and we create a new column named Next that contains the next event of the trace. We use this next column as a target value to train the model. To predict the time, we use the column current event as feature value and the time difference columns as target value.
Our final model is the random forest and prediction tree. We have developed a random forest. For the feature selection, we selected the most important features, event concept name, and event position. The position of the event in the case event trace. To avoid overfitting, we extended the random forest by bootstrapping the forest even further, particularly by incorporating bagging as an assembly method. Finally, the tool works with all available TUA datasets. The test and train data names can be given as input by the end user and a model will be executed automatically. It was decided not to use future data for any of the models, seeing as events are subject to various real-life changes such as data generating system changes over time.
Various improvements were made to the models. The CPT was improved by including the baseline prediction. The event subsequences were created by using the naive predictive values, and the subsequences were then used as the input and only training feature for creating the prediction tree and ultimately for prediction. This improved the accuracy immensely, reaching an accuracy of 43% on the no future test set, compared to its previous accuracy of 14.4%. The final naive estimator had an accuracy of 64%. It has an RMSE on the predicted time difference on the test set of 1.4 days. For LSTM, the accuracy was improved and error was reduced by putting more work into feature selection and hyperparameter tuning. The LSTM estimator was trained on 10 epochs. On the BPI Challenge 2012 dataset, it has an accuracy of 65.5%. For the random forest, The previous decision tree has been extended to a random forest to avoid overfitting and improve complexity of the model. Additionally, we try to increase the accuracy by optimizing the hyperparameters, particularly seeing some improvements when using entropy as the split quality criterion. Ultimately, we extended the random forest by bagging, bootstrapping the forest even further. It has a RMSE on the predicting time difference on the test set of 179.8 days and an accuracy of 71%.
When it comes to the results, the CPT accuracy score can be explained by the relation between the structure of the processes. As the CPT prediction process relies heavily on the process linearity, as it can only predict a new event, not part of the training sequence, this is therefore unfortunately not the most suitable option given the complex nonlinear structure of the process traces. For the LSTM, the accuracy was not improved further because the model sees the whole data file as one sequence instead of the different sequences. We could have improved this by reshaping the NP arrays and varying the batching size. This would have required for the cases to have the same amount of events as we have to reshape the numpty arrays. This sounded like a nice approach to resolve this problem. However, this would have taken up too much time to code as it is a difficult task to do. Moreover, we think that training the model would have taken a very long time, which is not what we aim to achieve. If we look at the CPU and memory usage of each model, we can see that the LSTM uses the most memory as well as the most CPU, thus being the worst in the area overall. Furthermore, there is a clear size difference between the CPU use of the CPT and LSTM, which is very high in comparison to the random forest and the EVE estimators. When looking at our best model, the random forest, it does use a lot of memory in second place to the LSTM, but it doesn't use as much CPU, having the second lowest amount of the four models.
The accuracy for each model was calculated as number of correctly predicted values over number of total predicted values, or, in other words, the proportion of correct prediction for event classification. RMSE was used as error measure for the models. This kind of measure is ideal in this situation as it measures the square root of the residual variance. By taking the root of the MSE, the RMSE as the same measure unit, showing how close our prediction were to the observed real values in a very intuitive and easy way to understand. One of the biggest limitations encountered was the time predictors, which are only applied to 2 of the 4 models, seeing that the remaining 2 are classification models. The random forest model performs the best in terms of accuracy and CPU usage, but its limitations are that it's not possible to calculate the RMCE and it uses a lot of memory compared to the other models. Overall, it is the best model amongst the 4.